All right, looks like some people are logging in. Can you guys hear me? Okay, great. Oh, looks like Diana doesn't want to hear us. It's actually kind of fun. I'm enjoying it. I'm finding myself getting a little distracted, but I guess that's kind of just how it goes. How about you guys? Reach. Nice. What's that? Oh, nice. Sweet. Started, eh? Whew. Yikes. That's a good start. Okay, that's better. I couldn't hear my own voice. Okay, are we ready to get started? Looks like we've got 1, 2, 3, 4, 5, 6 people in the chat. All right. I don't think anyone is watching it on YouTube. Is anyone? If you're on YouTube, can you just send me a little chat? Just say like, "Hi, I'm here." It says that 2 people are watching it, but I don't know if that's like me and also me. Okay, doesn't look like anyone's on YouTube. I'll keep it up just in case. And then when the nice thing about live streaming to YouTube is that as soon as the stream is over, then it's there. So if there's ever anything that you like forgot about or you wanted to clarify, you can always go back and watch the YouTube video. Did anyone? You know what? I actually need both of these. So did anyone? Oh, now my voice sounds so weird. These are like, what do you call it? Like noise isolating. So my voice sounds very strange in my own head. I don't, but it's like when your ears are plugged, your voice sounds strange. Like if you plug your ears and talk, my voice just sounds really weird. Anyway, let's get started. So just can you just let me know like if we're okay with partial fractions, or should I just start at partial fractions and then move forward from there? Yeah, that's pretty much it. Divide and do the thing. Just woke up, eh, man? It's like the afternoon. Brutal. Just as a little side note, don't forget about your personal hygiene, eh? I'm not making any accusations or anything, but I find that if you're stuck inside all day, it's really easy to forget to like brush your teeth and everything. So maybe after this stream, go take care of yourself, do some self-care, that kind of thing. Okay, so let's just do like a couple examples of partial fractions, because it is going to come up in this, and we're going to need to be comfortable doing partial fractions. So I'm going to just pull up a couple examples of partial fractions from our book. That's 10.3, I think. And we don't even really need to like do the whole integral portion of the partial fraction. I just want to like actually write this rational function I want to split it up into partial fractions. So are we okay with that? Are we good to go forward? It's so strange teaching without seeing any faces. I can't tell where you guys are at. I'm just like staring at my computer screen, talking. Yeah, he's good. Oh. Wait, do I have other people muted? Okay, hold on just 1 second. I think I may have muted some of you by accident. Okay. Okay, so let's do a couple quick examples. So let's okay, so let's write. Let's do this one here. I'm just pulling up kind of a random question in your book. Let's do and I'm altering it a little bit because I'm not too concerned about the integration because I know that you guys are good at that. So I'm just going to look at the partial fractions portion. So let's write this x minus 1 over x squared minus 7x plus 12 as a sum of partial fractions. Partial fractions. Okay. So when I do that, well, really what I have to do is I have to, I've got to factor this. So, oh yikes, now I have to factor this gross guy. I guess it's minus 3 and minus 4, right? Yeah. So, yeah. So I'll have x minus 3 and x minus 4. Perfect. So really what I want to do is I want to write this as something over x minus 3 plus something else over x minus 4. And when we're doing partial fractions, really all we're doing is we're just looking for a and b here. So there's quite a few different ways of doing it. The way I like to do it, you're kind of having to cheat a little bit. And what I mean by that is, like, if you really thought hard about what we were doing and you thought about like non-permissible values, this may raise some red flags. But I don't really want to get too bogged down by these details. I just kind of want to go straight to the answer. So the gist of it is that we're just going to multiply both sides of the equation by this thing right here. So in other words, I'll just change this to a different color. So this is what I'm going to multiply both sides of the equation by. And when I do that, then it'll just disappear from the left-hand side. And on the right-hand side, I will get, so this is just going to go like this. And on the right-hand side, I'm going to get x minus 4, and this will disappear. And on this side, I'll get x minus 3, and this will disappear. So in other words, I've got x minus 1 equals a times x minus 4 plus b times x minus 3. Okay, are we okay with that so far? Thank you, Nick. Okay. Okay, good. I mean, if by the way, I think the chat room that I'm in right now is in general discussion. So if you don't want to use your voice, you can always type a question or something like that, either in YouTube or the general discussion forum. Okay, so the idea here is that we're I mean, this has to be true for all values of x. So let's see what happens when x equals 4. Well, when x equals 4, this disappears, right? Because we'll have a times 0, and we've got 4 minus 1 equals, well, b times 4 minus 3 is 1. So in other words, b is equal to 3. And in the other case, if x is equal to 3, well then this thing would disappear and we'd be left with 3 minus 1 equals, a times 3 minus 4. So 2 is equal to negative a, or a equals negative 2. So we've solved for a, we've solved for b. So what follows is that our original equation, so x minus 1 over, what was it, x squared minus 7x minus 12, was that it? No, plus 12. That's equal to, well, a was negative 2. So we've got negative 2 over x minus 3 plus, and b was 3. Yes, b was 3 over x minus 4. Okay, and the whole point of this is that this would be very difficult to integrate, whereas this is really not that bad, because this is going to be some kind of natural log, and this is going to be another natural log when you integrate it, right? So that's partial, or not partial fractions. No, it is partial fractions. So yeah, we're gonna move on from that, because I'd like us to talk about the logistic function, and I can't think of either a better or worse day to talk about the logistic function, because it actually perfectly describes kind of what's going on with the coronavirus and its spread. So it's actually quite appropriate, but at the same time, like, I don't know about you, but I'm feeling like maybe a little overwhelmed by all this information overload that we're hearing about, you know, COVID-19 and all of that. So maybe this is like the worst day to talk about it, but in a lot of ways it's the best day to talk about it, because we're right in the middle of it. So let's talk about the logistic function. Okay, so the logistic function. So the logistic function is about sort of modeling population growth and other things related to that. So the logistic function. Okay. Okay, so I'd like us to consider. This this differential equation. So dy by dx is equal to k times y. So this is a logistic function. Sorry, not a logistic function. This is a differential equation that is often used to represent population growth, because so if this is some constant, so a constant k. So this is like, if you interpret this would be like the rate of change. So this is rate of change in y. So the rate of change in y, that would be proportional to y, right? That's what that means, which is basically how population growth works, right? So the bigger your population, the higher the rate of population growth there is, right? Like if you have only a few people, then it takes a really long time for that population to increase. But after you have a few billion people, then you don't even have to blink, and you have like many people being born at the same time, right? So so yeah, like as y increases, dy by dx increases. Now there's an issue with this. Well, by the way, if you solve this differential equation, we get that y is equal to y naught times e to the k times x, where y naught, this guy right here, this is the initial value of y. So your starting population, so your population at time 0, if you will. So this is great, and it's an excellent model, and it works really well. But there's a fairly obvious problem with this, and that this has no limit, right? So I think we can imagine that, you know, like if you had a pond, right, and you had some tadpoles in your pond, well, the population would increase quite a bit at first, but after a while, like the pond is only capable of keeping so many fish or frogs or whatever alive at the same time, right? So there has to be some kind of limit to the population. And you can imagine that as your population gets closer and closer to that limit, then the rate of change kind of starts to slow down and gets closer and closer to zero. Like the rate gets closer and closer to zero. So let's take a look at how we could maybe model that. So we'll have something that looks like this. Okay, where am I? Okay, so this is what the logistic function is. So we'll start off with a differential equation. So this is actually called the logistic differential equation. So the logistic DE, and it looks something like this. So we're still gonna model population with respect to time. So y here is our population, t is time, and we're still gonna have this this relationship. It is still going to be proportional to y, right? So it's going to be like as y gets bigger, the rate of change is going to get bigger as well. However, we are going to say, okay, so suppose the limit of our population is L. So suppose that we know that, like, no matter what, like on planet Earth, there's no way that we could ever, using all the technology that we have and all of the space that the world has to offer, we could never have, say, more than, I don't know, 20 billion people. I'm just making that number up, but you can imagine that there's probably some kind of hard limit that describes the maximum number of people that could live on planet Earth, or, you know, maximum number of tadpoles that can live in a pond. There's going to be some kind of hard limit that we just can't go past. So what we're going to want to do is we're going to want to sort of change the rate, so that the rate of change is going to be changed as we get closer and closer to L. And the way we do this is that we'll say that, okay, so we want two conditions. Okay, so when y is much smaller than L, we want this factor to be close to 0. Or sorry, be close to 1. Okay, so I'm going to start it off at 1, and I'm going to subtract something. The other condition is, so this is condition number 1. Condition number 2 is that as y approaches L, so as our population increases and increases and gets closer and closer to L, I'm going to want, so we want this factor. I'm talking about this factor that's in pink right here. So I want this to be close to 0. To be close to 0. Okay? So as y starts out, and it's going to start out small, we're going to want this factor to be very close to 1, so that we just have regular, like we'll be multiplying it by something very close to 1. So we have just regular growth that looks kind of exponential. But then as we get closer and closer and closer to that limit, we want that rate of change to get closer and closer to 0, because there's no way we can pass that limit. So let's write this. So the way we can write this is y over L. Okay? So the idea here is that if y, like let's say that y is like only 2 or 3, right? And then the population is, or the limit of the population is like 1 billion. Well, this is going to be like almost 0, right? It may as well be 0. So we'd have 1 minus 0, and we'd be multiplying that with this. So the rate of change is pretty much just exponential. However, as y gets closer and closer to L, like let's say that it actually is L, then we would have 1 minus 1, which is 0, and then we'd be multiplying this whole thing by 0, in which case the rate of change would be 0. So the slope, you can kind of think of the slope as being equal to 0. So this is called the logistic differential equation. So I mean, it's just a model. It's not a perfect model, but it pretty accurately describes how populations grow. As far as I understand, the way that you can change your model is kind of just by adjusting this. Like you can imagine that there's lots of different functions that that sort of start off at 1 and then end up going to 0 as y gets closer to L. But really all we have to do right now is just focus our energy on this logistic differential equation, because this is the equation that we're going to be using as our model. Okay, does that answer your question? Yeah. Okay. All right. Okay, what's up? Does L change? No. L is the hard limit. So L is kind of like the this notion of like you could never, like for example with like coronavirus, what do we have, like 7 billion people on planet Earth, something like that. So you couldn't have more than 7 billion people having the coronavirus, right? Like you can imagine that the closer and closer we get to 7 billion people having coronavirus, the smaller the rate of change would be, right? Because you can only have so many people get it every day after that, right? There's only so many people left. So the proportion of people who are even available to get it will be very small. Does that make sense? Okay. Now keep in mind, like in real life, this L may change. Like for example, if we were to model human population, like 1,000 years ago, there's no way the world could have been able to support 7 billion people, right? I mean, I'm no historian, but you can imagine that if we had 7 billion people, but we didn't have the infrastructure and electricity and sort of automation and all that, it'd be very difficult for planet Earth to be able to house so many people. So as technology increases, this limit can get bigger, but we're not quite there yet. We really all we're here to do is just take a look at the logistic differential equation and solve it. Okay. So does that answer your question? That's Crystal, right? Yeah. So does that make sense? Okay. Yeah. What's up? Oh, no, actually, that's a really good point. So if you're on YouTube, yeah, no, that's a good point. I even made a note to myself to repeat people's questions, but I forgot. So yeah, I mean, I guess if it wasn't already obvious, that last question was just, can L change? So if you're watching on YouTube, someone in Discord asked, can L change? And I don't remember the other questions, but yeah. Okay. And now people are laughing at me. Okay. Okay, so let's solve this then. So we're going to start off by separating the variables. So keep in mind that there is no t in here, but it's just going to make our life a lot easier if we keep this k on the right hand side and we move everything else to the left hand side, and you'll hopefully see where partial fractions come into play here. So I'm going to get something that looks like this. So I'm going to leave k on the right hand side, but bring everything else to the other side. So that gives me 1 over y times 1 minus y over L times dy by dt, and that's all equal to k. All right. Now I'm going to integrate both sides with respect to t. So dt and this dt, and this dt is going to cancel with that dt. So really what I'm left with is the integral, the integral 1 over y times 1 minus y over L dy is equal to the integral of k dt. And it's on that left-hand integral that we actually need to use partial fractions. So that's why I was kind of hoping that that you'd taken a look at partial fractions already. But really all it boils down to is just factoring it. And this is already factored for us, so we don't have to worry about factoring. But we can't really integrate this without some fairly sophisticated techniques. So we'll split it up into two fractions that are fairly straightforward. So let's focus our attention on this. So let's write 1 over y times 1 minus y over L as a sum of partial fractions. Okay. So when I do that, I'm going to have that 1 over y times 1 minus y over L is equal to a over y plus b over 1 minus y over L. Okay, so that looks okay. So the choices that I'm going to choose. Okay, well actually let's kind of bring this this portion up. So I'm going to multiply both sides by y times 1 minus y over L, and what I'll get is that 1 is equal to a times 1 minus y over L plus b times y. So I think that the natural choices for y would be, so I'm going to set y equal to 0. That would get rid of that term around b. So I'll have that 1 is equal to, 1 is equal to a times 1 minus 0, which is just 1, plus 0. So a is equal to 1. And then the other one that I would choose is I'm going to let y equal L. And when that happens, I'm going to have 1 equals a times, well, 1 minus L over L is 1 minus 1, which is 0. So actually I don't get anything over here. And I'll have L times b. So b is equal to 1 over L. Okay. So let's clean this up a little bit. So what we get is that this integral right here, the one that we started with, 1 over y times y, 1 minus y over L dy, that's going to be equal to the integral of, well, a was, what did we say, a was 1? 1 over y dy plus, and then b was 1 over L, so we got 1 over L times, or over 1 minus y over L dy. And this 1 over L business is kind of bugging me. So I'm just going to multiply the numerator and the denominator by L. And that should help clean things up. So times L. And we'll get something that looks really actually not that bad. So certainly this first integral is going to be fairly straightforward to integrate. So we've got 1 over y dy plus, this is, well, 1 over L times L is 1. And then this L is going to distribute. So I'll get L minus y dy. Okay, so we're getting somewhere now. So this on the left is going to be the natural log of the absolute value of y. And this is going to be, well, if I do a u substitution or whatever you want to call it, I'll get a negative because there's a negative sign in front of y. So I'm going to get minus ln of the absolute value of L minus y. Okay? And let's clean this up a little bit. Well, first of all, plus c. Thank you. Thank you. Oof, almost missed it. If we clean this up a little bit, well, using the log laws, we'll get that this is the ln of the absolute value of y over the absolute value of L minus y. But one thing to keep in mind, now this is, we have to remember what this is a model of. This is a model of population, and the population is never going to be negative. So we know that y is definitely positive. And furthermore, we know that L is the natural limit of y. Y can't get any bigger than L. So y is somewhere between 0 and L, which means that this, what I'm trying to say is we don't have to have these absolute value symbols. So this is just equal to the natural log of, y over L minus y. Okay. Now let's bring back the other portion, just the integral of k with respect to t. So we have that the ln of y over L minus y is equal to the integral of k dt, which is equal to kt. And I'm going to put the constant all the way on the right here. So I've got y over L minus y. Okay. So we're getting pretty close. Okay, let's see here. Where am I? So kt plus c, yeah, I've got that. And okay. So let's take everything to the eth power. So let's get rid of some of these logs here. So this is going to give me, well, I'll have y over L minus y is equal to e to the power of kt times e to the c. Okay, and now we need to figure out what this is equal to. Okay, so I'm going to say, first of all, I'm going to set a to be equal to like the initial value. So this is going to be e to the c. So let's just rewrite this as y over L minus y is equal to a times e to the kt. And let's figure out what a is equal to. So what is a equal to? Okay, so let's simplify a here. So let's figure out what a is, and we can do so just by setting t equal to 0. So we're just going to find the initial value of some of these terms. So if we set t equal to 0, well, the reason I'm setting t equal to 0 because ideally we would know the initial value of y. So in other words, ideally we would have some kind of idea of what our initial population is. So if I set t equal to 0, then not only do we have that initial information, but also this term is going to basically disappear, right? Because we'll have e to the 0, which is just 1. So in other words, a is equal to y naught over L minus y naught, where y naught is equal to the initial population, if you will. So like, what is our population starting at? Because you can't have a population that starts at 0, right? Like if you made up some kind of imaginary species with population 0, like they're not going to start unless you start it yourself. But just using just the basic principles of how population increases, you do need some population to start all of this. So that's what a is equal to. So we know what a is equal to, but we're just going to leave it written as a. But we do need to make a note of what a is equal to. We just don't want to have to write all this mumbo jumbo a whole bunch of times. So we still have to solve for y, because we do want to solve the differential equation. So we do want to isolate y. But let's do a little trick. So note that L minus y, hold on a second. Oh, yeah. Okay, okay, here's what we're going to do next. So I know that if y over L minus y is equal to a times e to the kt, that tells me a couple of things. Why don't we just sort of flip this whole thing upside down and see what we get? So I'm going to get L minus y over y equals 1 over a times e to the negative kt. And the reason we're doing that is just to be able to simplify this. It's going to be a little more tricky if the difference is in the denominator, but when it's in the numerator, it's a little bit easier to handle. And the reason for that is because this is equal to L over y minus 1. So in other words, I get that L over y minus 1 is equal to 1 over a times e to the negative kt. Yeah, it's equal to that. So our next step, we can have that L over y is equal to 1 over a times e to the negative kt plus 1. And now we're pretty much ready to solve this. Finally, I get that. Well, I'm going to just put this y over here, and I've got L over here, and the denominator is going to be 1 over a times e to the negative kt plus 1. And that's what we were looking for. So we've solved this this differential equation. So this is the logistic function, or the logistic equation. From here to here, like that. Okay, yeah, cross multiply. So the y came up over there, and this went down over there. Yeah. And I should put all this in brackets, right? Yeah. So that's our logistic function. I'd like to study this a little bit more over the coming days. But what I'd really like you to do is, excuse me, I got the hiccups. I'd like you to try to solve this again by yourself, and see if you can actually work through that algebra and that calculus, because it's going to be really useful to be able to do that on your own. And what I mean by that is that you could memorize this, and that's fine if you want to be able to memorize that. But if you take a look at that and it's not something that you're comfortable memorizing, it's a good idea to be able to work through the differential equation and be able to do it yourself, because there's going to be some questions where you just get a whole bunch of initial values of the population, you get the limit of the population, you get the proportion of how the population increases, like in that case that would be k, and then you'd have to derive that all yourself. Now, if you have the formula, then that's great. Then you can just use the formula and just punch it in, and then you'd be able to estimate the population at pretty much any given time. But if you don't have that formula, then you're going to be kind of stuck, and you're not really going to have anything, right? So it'd be a good idea to work through this a couple of times and see if you can derive this formula by yourself. Does that make sense? Yeah. You guys are so quiet. Usually in class, you guys are so talkative, but it's a little bit different now. You're all deafened. How far should you be? Well, I'm hoping that you're able to work through like the first couple sections in chapter 10. But I mean, obviously we're in a pretty unique situation here. So like if life is getting in the way, I completely understand. That said, we still have the same. I guess it's not quite the same, but we do have an AP Calc final exam to worry about. So yeah, so I think that it's as far as I understand, there's no multiple choice, which pardon me. Yeah. So as far as I understand, there's no multiple choice. It's all going to be what do they call those? Free questions or free response. So yeah, I don't really know exactly what it's going to look like. Have they announced what it'll finally look like? I guess we can check out their website. Yeah. Mm-hmm. Well, I suppose that if it's 45 minutes, then exactly, yeah. So by the way, if you're watching this on YouTube, we're just talking about the AP final exam and just some of the questions that we have about it. In particular, what happens if you have to pee. And we're kind of thinking that if it's 45 minutes, they might be expecting that no one gets a bathroom break, which is actually not unusual for some exams. I think some exams you're not allowed to leave under any circumstances for the first hour. So they could kind of be thinking of it like that. But yeah, I certainly have no idea what to expect. I mean, I've never. This is my first time teaching an AP Calculus course to begin with, and then let alone all these changes. Like none of my colleagues know exactly what it'll look like. I don't think that they completely know what it'll look like. I think that. Go on. My guess is that it would be live. So someone asked in the chat, who's going to watch the webcam footage? So if they do use a webcam to monitor the exam, I think the verb that they use is proctor. So if they do have a proctor, they'll probably watch it all live at once. Yeah, but they can probably assume that most, if not all, people have some kind of cell phone with a webcam functionality. Yeah, there's a lot of nuances. I wish I had more answers for you. I don't. My guess is that we'll be getting answers hopefully sooner rather than later. But yeah, I don't think anyone really knows what to expect at this point. So certainly the more I find out, the more I'll be posting. But yeah, like I said, I really have no idea what to expect. For homework? Yeah, so let's see if we can do 10.1, 2, and 3. And then tomorrow we'll talk a little bit more about the logistic function. I've got a few links that I'd like to share with you, and it'd be fun to sort of play with it a little bit more. Maybe take a look at the slope field for different logistic functions, and yeah, take it from there. Okay, so someone on the chat is pointing out that they stated that they were limiting the technology required, so likely no webcams, to enable rural areas with bad internet connections to still be able to compete. So yeah, no kidding. I actually, for all of this, I had to get a completely different internet provider because I had MTS before, and my upload speed was like, if I was lucky, I would get 2 megabits per second up, which is not good enough. Yeah, so now I'm with Shaw, and I have 20 megabits up, which is perfectly fine for streaming. But if you don't have that, then yeah, I'm not sure how else you would do it. Although I guess they wouldn't really need the best connection. Just like even a 1 frame every 30 seconds or so would probably be enough to monitor someone. But even so, there's just so many questions about this. So I wish I... True. I mean, I saw a meme the other day of someone kind of in this situation, and he had just had a recording of himself frantically writing notes, and he had that sort of like on loop on his camera, and then he had that, on his phone, and then he had his phone in front of his laptop, so that his laptop webcam was just recording him taking notes, but then he was sitting beside all of that, and he was just playing video games. So I'm and I think it just sort of, I mean, it was a joke, but it also sort of brought up the notion of like, okay, like how secure is this? Like, this seems like a pretty easy thing to, take advantage of. Mm-hmm. Yeah. 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 And anyway, what they're saying in the chat for the YouTube people who are watching is just that there's a lot of different ways to cheat. Someone asked, is a 5 on this exam going to be the same as a 5 on last year's exam? I'm not really sure how much that matters, because really the people who you're competing against for scholarships and whatnot are all going to be writing the same one this year, right? So we'd all still be in the same boat. But yeah, I mean, absolutely, it's a very good question, and I have no idea what the answer is. So yeah, it looks like Riley's got a lot of information here, so you can check out the chat here. Yeah, so take a look at that. Hopefully we'll get more information as the days go forward. But yeah, certainly if I learn anything else, then I'll post about it. Mm-hmm. Yeah. Yeah. No, but I imagine that they have a pretty good idea. I mean, it's not their first time that they've done this, right? So, I mean, it's the first time that they've done it online, but I mean, typically the way they do it is that they would just time themselves writing it and then multiply that by some constant. I mean, these are, you could probably write some kind of differential equation to calculate the amount of time it would take a student based on, an expert's time. So my guess is that that's how they identify how long questions take. I know that for me, what I do is if I'm making an exam for the first time and I want to see if my students are going to be able to finish it in time, I time myself and then I multiply that by 3, and that's typically enough time for the average student to complete an exam. So what they do? Yeah, so like if it takes me 20 minutes, then it probably takes a student 60 minutes. And of course that depends on a lot of things. Sometimes I might have to multiply that by 4. Like when I was in grade 7, I'm way faster than grade 7, so I would usually do like times 4 times 5. But for like a grade 11 or a grade 10 test, then yeah, about times 3. And for you guys, I already have tests are ready to go, so they've already sort of been vetted, and you guys have 2 hours. So yeah. Okay, so just to repeat the question, so how is this going to affect our grade? Because our grade is pretty much all tests. Well, I've sort of been experimenting with different pieces of software that would, I guess I would just kind of move to an assignment model instead of a test model. So just give you some assignments, and I would mark those assignments, and those would just kind of take place of what we would do for tests, because I'm not really going to worry about doing tests right now, because it just seems like more stress and more unknowns and more complications. So we'll kind of go to an assignment model. I think I figured out what the software that I'm going to use is, but I don't want to say anything because I don't want to have to contradict myself. So I've got a pretty good idea of what the software is, but not entirely sure if I'm going to use it yet. Yeah. So as far as I understand is I could do like a few multiple choice questions, in which case that would kind of be like you get immediate feedback. But another thing too is there is the opportunity to do long answers, and you would just photograph your work. Pardon me? Yeah, so I could probably use that, yeah. And I've been looking at a different piece of software because I would like to be able to ask my own questions. Yeah, so as far as I understand with a free response is that you take a photo of your work and then you upload it. So I guess that would be another argument saying that, yeah, you actually do need a webcam for this. But like I said, I could have a misunderstanding about how that works. So I don't know. So these are all valid questions. The question was, do we get extra time because we'd have to spend time photographing our work? I don't know. I know that it's probably a good idea to practice doing this a couple of times beforehand. So if you haven't been using the progress check, now would probably be a good time to try it out. Because my guess is that whatever solution they do use, it'll be similar to what they already have. So on the AP Central, I have unleashed I have released some of the progress checks, so you can try some of those. Maybe I can start doing that a little more often. So maybe once a week, I can put a new progress check, so you can check your progress and try the digital learning system that they have. But yeah, these are all very good questions. I wish I had more answers. But yeah, in the meantime, I'm gonna sign out because I have to prepare for my grade 11 class. And if you have any questions, send me either like an Instagram message or email or a message on here. I'll try to monitor it as close as I can. But I'm sure you can imagine I'm getting lots of emails nowadays because that's really the only form of communication. There's no more face-to-face communication, so I'm a little backlogged with my email and stuff, but I'll do my best. And can you see me anymore? No. Oh, okay, but you can still hear me. Yeah, so just stay tuned, and if you have any questions, post them on here or email or whatever, and I guess I'll see you next time, eh? Exactly, Monday to Friday, just like a regular class, but we'll be taking a break over... All right, better late than never. Anyway, I'm gonna sign out. I'm not taking attendance, but I am counting how many people are present because we do have to report the audience that we're reaching. So I'm gonna take this attendance and I will count however many views the live YouTube stream got, and I'll add those two together and I'll report that number to Mr. Hutchison. Yeah, I'm going to pretend I'm not seeing that. Anyway, I will talk to you guys tomorrow, and leave me a message if you have any questions. Bye-bye.